Okay. Welcome everyone online to the special edition MLBBQ. Today is going to be a lot more of an unstructured discussion style where, I don't know, some social events happened. So for one, someone on Twitter named Isaac King said, recently met a guy excited to tell me how Cantor's diagonal argument is wrong. Concerned he was a crackpot, but I heard him out and turns out he was totally right. Okay, the actual argument is correct, but most popular explanations of it are wrong. I'm assuming this person was talking about the actual Cantor's diagonal argument. But for context, does everyone here know what Cantor's diagonal argument is? Okay, so we will consult our favorite LLM, Google, Cantor's diagonal argument.
If you press OK.
Yeah, there we go. Okay, so this is an illustration of Cantor's diagonal argument. It is a proof for the uncountability of the reals. Said differently, it can also mean that there is no bijection between the natural numbers and the real numbers. And the way it works is instead of, usually you prove, actually before that, does everyone here know what a bijection is? One-to-one correspondence. Right. One-to-one correspondence is the set theory interpretation. Another way of thinking about bijection is the existence of two functions, the one going to the left and one going to the right. So go from natural number to real and go from real to natural number. Now, it's a reversible function. Yes. So reversibility falls out of bijectivity. Okay. So it's pretty trivial to construct a function that goes from the reals to the natural numbers. That part's easy. So this is surjective. There's a surjective relationship between the natural numbers and the reals. However, the injective part is really hard. So injective part is really easy. Surjective is really hard. How do you get a unique real number from every natural number? And this proof is showing that it is impossible. So first, you construct a bunch of natural numbers. Specifically, these are supposed to be interpreted in base 2. And the way that you do it is you just randomly generate a bunch of zeros and ones. So you do this for every single possible natural number. And now what you do is you go along the diagonal and you do a bit flip. So it is different from every single natural number at least.
You're kind of jumping ahead, I think. Like the numeration.
Enumeration
is that column. You just enumerate.
Yeah.
You go from 1 to infinity. That's your enumeration.
Yeah, you go from 1 to infinity as an enumeration of all the natural numbers.
You can be systematic about.
Yes, you can. You can also.
The binary representation of mantissa. We're only enumerating numbers between 0 and 1.
Yes.
And yeah, so whatever is written there is after the dot, the decimal dot.
So there's infinitely many of these, and because we're interpreting things after the decimal point, you can interpret this basically as also the set of all the rational numbers too, because it's every possible thing in between 0 and 1. Right, this is big enough to store all the rational numbers. Okay, here is where the things break down. You go along this diagonal, and then you flip all the bits. So it is different from every single rational number at some point, okay? And then you also need to prove that this is actually a real number, not like a divergent sequence. But then, simultaneously, yes?
If you flip those numbers, how are you sure that it become one of the numbers that is already somewhere?
Because eventually, that number will also have a flip on it. Oh. So it's tautological. Yeah. It will be different from every single number.
But that's the proof already.
Yeah.
So the proof is by contradiction.
So you might find this kind of strange. Pavel actually has a point, which is how do you know if this thing right here, this diagonal right here, can actually be constructed? Is it even meaningful to have a number that actually differs from every single rational number at some point? Is that even something you can construct? So when Cantor first made this argument,
but that's not what it claims. It's just it doesn't claim it's different from every single. Oh, you said rational, natural. Well, okay.
Same thing. For if you interpret it as for this argument, it doesn't really matter because both of them are countable.
Yes, yes.
Yeah.
Okay, but anyways.
Yeah. So when Cantor made this argument, the contention was that this was actually a real number, and this proved that there was some number, at least one of them, that is in the reals but is not in the natural numbers. Therefore, the real numbers are not countable. To be countable means to have a bijection with the natural numbers. So for example, things that are bijective to the natural numbers are memory addresses in your computer, the number of people on the planet, number of dollars in the Federal Reserve. That's infinite, but it's still countable.
Even if we keep printing.
Even if we keep printing, it's infinite, but still countable. It's still going to be some number that is in correspondence with some natural number. So rational numbers are also countable. Yes, it's not immediately obvious how to count them, but they are countable. They're you have to do a double for loop and whatnot.
No, but it's kind of beautiful how rational numbers are countable, but it's just a simple matrix as well as this one.
Yeah. Okay, here's the thing. This argument right here also somewhat shows up in Turing's proof of the halting problem. Yes.
Rational numbers are countable.
Yeah, rational numbers are countable.
Based on definition, I checked it because I'm not mathematical background. I know it's infinite, but it can be have like a 1-to-1 correspondence.
Yes.
Can you just pull out?
Yeah. So
That's easy.
dovetailing rational numbers.
No. It's a good question. Like for context. Yeah, this one, right? No.
Which one? Yeah. So the definition of what it means to be countable is that there is a bijection with the natural numbers.
But can you show that Mike matrix?
Which one?
This one.
This one?
No, it's not the matrix.
This one. Yes. Okay, yeah, here we go.
So just write all of numerators as columns and denominators as rows, for example. Just natural numbers from 1 to infinity, and everywhere around their intersection will be this divided by that.
Indeed,
So,
and you can use a space filling curve to fill out the square.
yeah,
and then you're done.
So and then 1, 2, 3, 4, 5, you count them like that. So you count them to infinity, you can count all of them.
So there is a scheme in which you can turn every single rational number into some corresponding unique natural number. But that's not what we're here for today. What we're here for today is the fact that there is a hidden connection that people don't know about between this argument that we all know and love, the halting problem. Everyone here is presumably familiar with the halting problem? Okay, I give you an algorithm, a block of code. Can you tell me it will terminate or not? Is there a procedure by which you can tell me whether or not it terminates?
We need a good theory class.
We do. We really do need this theory class.
Good, simple.
Yeah.
Interesting.
Yeah. This problem spawned the field of computer science. It was Turing's answer to a problem from Hilbert, and for that he invented Turing machines and simultaneously proved the halting problem. So this is kind of like if we were Christians, it would be equivalently the birth of Jesus, basically. Yeah, this was the problem that spawned computer science.
I'm not sure the transitive property applies to that, but okay.
Well, the thing is, when we talk about computer science, we talk about Turing, we talk about Turing machines.
It's because we don't want to talk about the Paleolithic time of computer science, Leibniz and others.
But that back then was more like procedure theory and didn't resemble what we would call computer science today. Like,
I mean, it was foreshadowed heavily.
Yes. People understood it at the time, but it wasn't put into a coherent picture until Turing. So the field didn't form until Turing did.
The modern notion of the field, which will also be transformed.
Yeah, exactly.
But yes,
similar to how physics was done for thousands of years, but it was called natural science or natural philosophy. It wasn't called physics until like Newton and afterwards. Even Newton himself considered
No,
him.
it was all natural philosophy. I don't know when actual word physics came up.
Really?
Yeah, I don't think it's new.
Okay. So it also shows up in halting problem, the beginning problem of computer science. It also shows up in Russell's paradox. Everyone here knows what Russell's paradox is? Set of all sets. Set of all sets that don't contain themselves.
The barber is easier to.
Barber is also like that, yeah. Russell's paradox is a bug. It's a documented bug in naive set theory. Naive set theory allowed you to do unrestricted comprehension. So a set can contain anything, including itself. And not only itself, but also itself and also not itself simultaneously. And that's the problem. So because naive set theory let you express any predicate as part of its membership, you can describe a paradox basically inside of that predicate. And that leads to a soundness issue or a consistency issue in naive set theory. So if you construct a set of all sets that don't contain themselves, if you think about that statement, right? If it does contain itself, so either it has to contain itself or it doesn't. Now, if it does contain itself, then that's a contradiction because it says that it doesn't contain itself. But if it doesn't contain itself, then it doesn't contain itself. So it must be within itself because the definition is all sets that don't contain themselves. So it's a contradiction. It's a way of encoding a paradox inside of set theory. So set of all sets that don't contain themselves. Maybe there is a picture. I don't know.
It sounds like a Venn diagram that overlaps it and has like a.
It'll be a very strange. It'll be a very strange Venn diagram.
Yeah, this is an impossible set.
Yeah.
What do you mean?
Yeah. The issue is that it's impossible to draw. Also,
Yeah.
given that it's a paradox, you can't construct the correct picture for it. Okay, so all of these things.
No, but the most important one for the pop science is Gödel's.
Oh yes. Gödel's incompleteness theorem. Anyone here actually know what it says?
Oh, which one?
The first one. Yeah. The second one people are more familiar with. Do people know what the second one says? Okay. So the first one says, the first Gödel incompleteness theorem says that there are some statements, some mathematical statements, which are true, but nevertheless cannot be proved. By the way, this is wrong. That's a wrong translation of Gödel's incompleteness theorem. The simpler statement is just that there are statements that cannot be proved. That's it. You cannot even say that they are true. There is no notion in which those statements that cannot be proven are true.
Well, they can be. Well.
They are.
Okay.
Yeah.
In me being Thomist, as you said.
Yes, if you were Thomas.
They may as well be true.
Right. But the reference.
We'll never know.
Yeah, but the reference frame for them being true does not exist within the mathematical language. It exists outside of it. So we say it's true, but the language that can't know it's true. The second one is of the statements that cannot be proved within a language, the statement, this language is consistent, is one of those. So no language can prove its own consistency. Consistency is the inability to derive false. You cannot prove a false statement.
Lack of contradictions.
Yeah, lack of contradictions. So that's a second one. So the first one is a generic statement. The second one is a refinement of it, specifically for one very important statement, that being this language is consistent. So very, very big concern because that was the whole point of this guy, Hilbert. Hilbert's.
He had 20-some points.
But this is the big one in his program. It's called, okay, repeat, say it with me. Does anyone know the name? Oh, so sad. The Entscheidung problem.
Yeah.
It's the decision problem.
Decision.
So it's the problem for any universal algorithm that can determine the truth or falsehood of any logical statement within a formal mathematical system. Let's say your statement in question is like the infinitude of the primes, right? Let's say, is there a procedure by which you can plug this in and figure out if it's true or false, right? versus something like the Riemann hypothesis. You can plug it in and see if it's true or false. Okay, we know now today that this is obviously false. Trivial counterexample being the halting problem. Every computer scientist knows of the halting problem. There's no procedure that can tell you whether or not a particular program will halt or not. So that is one such program that is either true or false, but you cannot have a procedure or an algorithm that tells you whether or not it is true or false. It may be true or false, but we can't decide it. And that's why it's called the decision problem. It's undecidable.
You are talking like a marketer that sells the things that you are just going to refute, because it might as well be, but that all interesting programs, we can know when they halt or not.
It depends on what you mean by interesting. Whether or not a program halts is a very interesting problem.
Well, not okay.
Right.
This is kind of the non-interesting problem, or the interesting problem that we can exclude. So
there's some of them are not interesting. So many other problems that are interesting, obviously interesting, but we cannot actually have this algorithm. For example, termination of merge sort. There is no algorithm that can tell you whether or not merge sort will terminate. You have to settle it with a proof. If you try writing merge sort
for every data set,
for any list, yeah.
We'll just run.
That's not a proof. That's test. It's something different. Epistemically different. It's strong, but still different.
Well, what do you mean? Why do you need to prove every data set, but that's equivalent to by construction?
Oh, no. You're not proving it like for any given list. You're doing something a bit more sophisticated. You have to set up a measure for the length of the list and show that the measure is terminating. The measure goes to 0.
For what? What is the restriction?
The restriction
for lists of this type.
Yeah, for lists of this length, show that the subcalls of merge sort calls it on a shorter and shorter list and will actually hit 0. And when it props back up, so for the split and the merge, both of them terminate. So you have to do 2 proofs.
Yeah, but that refutes this. That means you can know whether it holds or not.
No, you've proven it, but you didn't derive it via an algorithm. What Hilbert is saying is there a machine that can prove it for you, and that machine does not exist.
Well, automatic provers, why not?
Huh?
Yeah.
Are we this machine?
Yes.
No, we're not.
Yeah.
It's no. For simple algorithms, there are heuristics that we use that get us to the answer, but it is not a decision procedure. You don't know what you will write down next. It's a much more sophisticated process than a simple algorithm.
No, if you can do a proof, that means you are the machine deriving that proof.
This is true in a heuristic sense, and if you are Roger Penrose, this is very compelling. But from a formal perspective, it's not very compelling, because what is the algorithm?
No, Roger Penrose is quite opposite. He introduces spooky notions and all that. But from a simple perspective, we are the machine.
Yeah, but how do you describe the machine? It's
I point to it.
This doesn't work. It's as lossy as a sampling like a random number generator and saying that because eventually when you sample the random number generator.
No. I totally disagree that, but that's a different point of this is about this sampling LLMs. I have an idea that it's a wrong approach.
I see.
We can discuss about this.
Okay, so all of these problems right here. There is actually a unifying principle for all of them. And I explained in my seminal work, Lawvere's fixed point theorem and the devious diagonal. So,
well, to be honest, people know about that.
Yes. My
people like
my presentation of
the
it.
collective know this result, but still, I mean, it's a very cool presentation.
Yes.
Fantastic.
So it's a rephrasing of Lawvere's fixed point theorem. I just stole it. Yes, I basically stole it.
Well, you didn't steal it. You told us about it.
Yes, indeed.
In a fictional serotonin. Yes. Kind
Lawvere's
of inducing style.
Yes, indeed. Lawvere's fixed point theorem 1969. I, for some reason, cannot find the actual PDF of it.
Oh, you said one single page.
One single page within that paper, yes. I can't find the actual PDF, but
Yeah.
whatever. Okay, so what is it? What is it? What is it? What is it about? So it is about this thing called the diagonal. Oh, I know what it is now. Cartesian categories and the diagonal Lawvere. And yes, this one. This
I
one.
was confused by the naming.
Hmm?
Yeah, I was confused by the naming because you act revelational, like, hey, the diagonal, but I don't see the diagonal. And then so I had to dig a little bit and figure out why it's called diagonal, why the product is called diagonal.
Yes, it's via the product that it's called diagonal. Okay.
Well, but yeah, you will have to, I think,
Oh,
dive
God.
a little because
Oh, God.
my comment there.
Indeed.
about that.
Indeed. So let's go on my favorite website, Excalidraw. Maybe that was a bad open for the Excalidraw app. So anyone here know what a category is? Sergey, do you want to give them a demo on what a category is?
No idea. It's
Okay.
a point in a graph from my perspective.
Okay. So a category. What's a category? Category theory. My God. Okay, so category. That looks kind of scary. Let's not do that. Let's do this first. Okay, this is a good picture of what a category is. So a category is a bunch of objects. That's A, B, and C, plus some morphisms like F and G, such that two properties hold, two very important properties. The first is that every single object has a unique morphism called identity that maps from it to itself. It's a self arrow. All right, Sergey will love this. And so A has one, B has one, C has one. So these are fixed points. No matter how many times you apply identity, you get to the same place. Very interesting. The next rule is associativity. Ignore the fact that it's not really the associativity that you know about, but it basically says that if you have
No, it's practically the same. It's function application.
Okay. Kind of, yeah. So if you have morphisms F and morphisms G, there exists a morphism that goes through. So this goes from A to B and this goes from B to C. There must exist a morphism that goes directly from A to C. That is just the composition of F with G.
It's like in linear algebra.
It's like in linear algebra.
So what are A, B, and C again?
It doesn't matter. They're just objects. So
F is a mapping.
yes, F is a mapping. So you can interpret this as types. Let's say that's an integer. Let's say this is a string, and that's a list. Right?
It's just an abstract notion of things and relations.
And relations between them that satisfy two very fun properties. First, that there exists an identity map, and second, that things compose. So causality? No. We are like 2,000 years away from a notion of time.
Yeah. Double check.
Yes. This is a purely structural notion. There is no like physical connotation. There's no like physical analogy. Like things aren't being like moved in a direction or whatever. It's just a thing. So if you slap an F in front of the A, you can collapse it into a B. It's pure algebra, purely symbolic. Does that make sense? Okay. So
It's just so loose that it can mean anything you want.
So on the notion of looseness, I wish I could use the board, but
Well,
people
because
online won't see it.
yeah, it will come up FG. They can also be in a set of objects. You can take all the F's and G's there and put them as objects. Right? Even
Yeah.
though they are not objects, they are verbs in a sense, right? They're relations.
They are
But
yes.
relations can also be
Yes.
Objects.
Yes.
So anything can be an object.
Anything can be an object, except objects aren't actually real. The thing that's real is the morphisms.
Well, morphism is the correspondence,
Mhm.
or what is morphism in this case?
So
Right, relation.
it's a relation. So let's give an example of one such interesting category.
Sorry, online people.
Sorry, online people, but we're gonna have to move to the whiteboard to make sense of things.
Well, if you
So-
turn your camera on, I can point it to you.
Oh, that's interesting. That does work. Zoom. Where is it? Video. Oh no. Can I not turn it on?
Permissions.
Maybe permissions. Did it?
It did.
Okay.
Oh, you're not sharing.
I have no idea. I have no. Okay, wait, we see it.
Oh,
on
but
the-
stop sharing. Stop sharing.
Oh, I need to stop sharing my screen.
Then they will see you.
How do I?
The green button. No,
Stop
red,
share.
yeah. Okay, now.
Lovely. Everybody's over here instead. This board is way bigger.
Yes.
Okay, cool. So, one interesting category that everyone cares about is the category set, right? In set, you have sets A, sets B, and sets C. Anyone here can tell me what's the most interesting thing you can do in set theory?
Oh, pick an object.
Wrong. Wrong.
Power set? No.
Wrong.
Count set.
Count sets is also wrong. Removing is also wrong. What is the most primitive notion of a thing you can do in set theory that everything else is defined off of?
Add an object.
Join.
No. Membership.
Oh.
Membership.
Oh, but that is like pick an object.
It is not like pick an object. It is actually the opposite of picking an object. It is saying that the object is part of something else. You're not picking it out. Picking it out is way harder. So you have A is a member of B, and B is a member of C, and so on and so forth, right? Okay, here's some more interesting things. Maybe membership is the wrong one to use here. Let's use subset instead. So we'll talk about membership later, maybe not today, but right now let's just talk about membership, right? So A is a subset of B, and B is a subset of C. Here's an interesting question. Is A a subset of itself? Yes, it is. And is it transitive?
Well, why did we invent
It's not a proper
a
set.
proper subset? It's not a proper subset. We have invented the equality there, right?
Mhm.
It's subset equal.
Sure.
So it is not actually. A
Yes, it's not a
subset.
proper subset, yes, but it's possible that it is either equal to A or less than A.
Yeah.
Yeah, so the two properties you care about here are symmetry or reflexivity first. Reflexivity. A, like so. The second one is symmetry. Actually, do we have symmetry? We do not have symmetry yet. We do have transitivity though, which is A subset B, B subset C implies A subset C. Oh hey, that's the thingy. A, B, C, like that, right? Category. So this models categories model a very important thing that we care about a lot in mathematics. That thing being something that looks like that. This is an order theoretic notion of mathematics. These are relations in mathematics. We care about properties like reflexivity, transitivity, maybe symmetry. A like that implies B is like that, but that's not true for the case of category theory. So A has a morphism to B doesn't necessarily mean that B is a morphism to A. Same thing here. So only these two are important. And in a sense, this is as loose as you can go mathematically and have things still make sense.
So what is morphism? Is it like any kind of operation?
Relation.
Huh?
Morphism.
It's a relation, yeah. It's a relation that can, yeah.
And does it have to be the same kind of relation between A and B and B and C? Like if we're talking right now about sets.
So in thin categories, kind of, the relation have to be somewhat of similar sort. But in categories proper, they don't actually have to be of the same type at all. So you can also interpret like this. You have an int, you have a string, you have a list, right? And this is the composition of them. And that's how function composition works. So it models a lot of things that we care about. It models types in a type language. It models sets. It models groups. Models monoids. Like all these different mathematical structures. So the one that we care about today, as it relates to Lawvere's theorem, are two things. The first one is the categorical product. So anyone know what a Cartesian product is in set theory?
All possible combinations of the sets.
All possible combinations of elements within two sets, right? So you have A, you have B, and then you do the Cartesian product. Let me just use this.
So which class is that here in CS?
I don't know, I didn't take it here.
Yeah.
Yeah. Is equal to A cross B,
Don't tell me.
right?
Doesn't belong there.
Which is the pairing of all possible things from A with all possible pairings from B. Cool. So this is fine, but it's a bit strict. It's a bit strict simply because, well, I don't want like a completed thing necessarily. What I care about are two things. I should be able to get an A back out, and I should be able to get a B back out of it. Right? Think of this simpler as like a tuple, like A and B. And indeed, a tuple in programming languages is the most primitive notion of a product you can define without using like more sophisticated machinery. It's a thing that if you have both A and B, you can obtain. And once you have, you can reobtain an A, or you can get a B. Does that make sense? Like any sense at all?
If it was numbers and multiplication, then by multiplying A and B and by dividing by B, you get A again.
A multiplication is a bit weirder. Anyone here took abstract algebra or like some equivalent? So the way that multiplication works in, say, like in abstract algebra is when you take the number 6 and you multiply it with 2, the thing you get first and foremost is the product 6, 2. So 6, 2 first. And then you use a special thing called an equivalence relation to collapse this down into 12, such that 2, 6 also collapses down to this. And also 3, 4 also collapses down to this. So when things are equal algebraically, what it means is that they are equal under this equivalence relation. But prior to this extra piece of machinery that is the equivalence relation, what you first have is the pairing thing. And the pairing thing exists in all notions of the category of the product. Same thing also with set theory. Before you get the notion of this bigger thing that contains all possible pairs of A and B, you have miniature pairs A, B that are elements of A and B. Does that make sense? The thing you're constructing is a tuple.
But what Pavel was asking, I think, is that it's impossible to extract 6 from 12.
Oh, yes. Well, that is because equivalence relations do not have to be reversible. However, products are, right? Just pairing two things together is very much reversible.
I just don't understand what these two lines meant. A times B goes to A or B.
It's what makes a tuple useful, right? If you make a tuple in, say, Python, and you are unable to extract out the two things you put in, it's a useless tuple, right? To make it to be.
But you can save a byte.
Huh?
Instead of storing the tuple in 2 bytes, you can store it in 1.
Store it in 1 byte. That's a different thing. That's called a coproduct. So the product is defined by this thing called a universal property. We might honestly be going too far by talking about it, but that's okay. Let's just try it. And then A, and then B, and then first and foremost we have these things, project 1 and project 2 that we care about. So those are the first two things we care about that I already talked about. The thing that we want from a product is the fact that we can factor it back to the thing that we used to make it. So we got A and then we got B. In addition to that, the property of products is such that for any other object, C, which also has a projection map into A and B, it is still not fully factorized. There is still another morphism, like hiding here, that turns it into an A and B. So said differently, the product is the most compact possible thing that can do this factoring trick. let's say another thing that might be a product is like I have A, I have B. I just make a tuple that's just A, B, and also the number 0. Right? And then from this, you can extract out an A. You can also extract out an B. But there are other things you can do with it. It's not fully compact. The most compact thing would be also removing the 0 over here. Does that make sense? It has to be the minimally compact thing that stores A and B. Right?
And C can be bigger.
Huh?
And C can be
Yeah, C can be bigger than just A and B.
That makes sense. Otherwise, it would just be.
Exactly. Yeah. Otherwise, you can encode for like ridiculous information inside of it. Yeah, exactly. So for something to be a product, it has to be minimally compact to contain A and B. So that's the product. Now, here's the funny thing. The categories that we usually care about live in this world that we call Cartesian. I won't tell you exactly what Cartesian means, but Cartesian in our context means that we have a product and some other things, but the product is the one that we care about. And also, we can do this one trick. So given that anything, let's just call this a blob right now, anything that has 2 morphisms going from the first guy, squiggle 1, and also another morphism that goes to squiggle 2, satisfies itself as the product. What if you can construct a guy that is A cross A? Then you have one projection function that goes to A, and another projection function that goes to also A. In fact, these 2 can be equal. I never said these 2 have to be different, right? So these 2 morphisms can be equal. So now you have A cross A, and to get a pair out of an element, it's also trivial, right? If I give you an int 4, getting a int cross int is very easy. Just make it into a tuple. You don't need a second element, right? Very simple. So this A cross A is a valid product. And this guy right here, this is what we care about. This is called the diagonal. Right? You might be wondering, big deal, who cares? Like you can duplicate a thing. Okay, I can duplicate a number.
Tell us why it is called diagonal, so we immediately say, okay. Everyone sees why it is called diagonal.
Cartesian product.
You think it's a good picture for the diagonal.
It is an intuitive name.
Categorical diagonal.
Because back on the old photo, it loops back around to the original one. Is that why it's called it?
No, but why is this diagonal?
It is a diagonal. Yeah, it's a diagonal morphism.
Well, it's called diagonal because if you look at the matrix, or if A is set of reals, if A is set of reals, this is a plane, and this is y equals x. It says take an element from a line, and you will get.
Oh yeah. If you take this as a real,
and it
real
will
numbers,
literally be 45-degree diagonal.
Yeah.
If it's a matrix, it also will select elements with the same index. So like, no matter what it is, it will sort of be in that sense, it's diagonal. So it doesn't have to do anything with the proof that Mike started with. And that confused me, for example, because like the name is the same, but the sort of the semantics why it is this is different.
Yes, indeed.
Can I put a question? Is it in any way related to like if you assume that A is a vector, then A is like an outer product of that?
It's just an outer product. The outer product is defined via this product. It requires some extra machinery.
Okay.
Yeah. Because you need something to take a pair of vectors down to an element, and all the magic of the outer product is stored into the how of how you collapse that. But the initial step is the same.
But they will be all rank 1 on the diagonal.
Rank 1 on the diagonal.
If you're getting those matrices,
Oh, I see.
and you're kind of like, oh, I'm creating a space of matrices of n by n matrices from a space of n vectors. But those are special, the diagonal matrices.
Indeed.
They're not diagonalizable or anything, but they are kind of on a specific direction of that n squared space, on the diagonal of that space in a sense. They rank one. They're all just a vector.
Yeah.
Stored in the matrix.
Stored in matrix.
Yeah, there's like they have a rank one.
So what is the point of the pi one and pi two?
Pi one and pi two are functions to extract out elements from the product. So in a tuple, this is index at 0 and index at 1.
Was it blob or is it pi? Sorry, I want to make sure.
Blob.
Oh, pi. Sorry.
Yeah, pi. Yeah.
I didn't
What
see
is your relation, morphism?
Yes.
We're gonna be learning this vocabulary.
that. Sorry.
Soon the children will all have to start discrete
Yeah.
math by learning what a category is.
Yeah.
Okay, so you might be asking, why do we care? Why is this important? Like, why is it at all scary or leads to like 5 different paradoxes? The issue is that not all objects are as well behaved as a number. Take, for instance, anyone know lambda calculus? Do we know what this means?
It's a function applied to y.
It's a function applied to y. So this guy, this thing right here is called lambda expression. This is the argument. This is the body. And when you apply a symbol to it, you replace the argument with the thing. So this turns it into y. Right? If I instead use yy, then it would turn to yy. If I instead had instead of x, I had xx over here, then it'll duplicate y a bunch of times like that. Right? Does that make sense?
It's just definition of the same thing.
You eventually will see. Yeah. So you can define lambda calculus inside of a Cartesian category. In fact, Cartesian categories natively include a model of lambda calculus. So there's hidden within the kind of logic that we care about a model of this guy. So
Lambda calculus is something special to
Huh?
Computer science. That's another Jesus. Jesus turns like
Yes,
that,
yes, yes,
and you
Jesus.
see
yes.
on the back of his head is church, and on the face is Turing.
Yeah, so anyone who's seen like the Holy Trinity, Cartesian science has one too, and it's Turing. I spelled the same wrong. Church
Okay.
and Gödel. These 3 guys created the 3 initial universal computers. Anyone know the one for Turing?
It's Turing machine, right?
Turing machine.
Yeah.
That was a hard one.
That was a really hard one.
Sorry.
Okay.
Where's Ada Lovelace?
Ada Lovelace did algorithms. She did not do computers.
That's fair. Okay.
Yeah.
She had the
Well,
Lumi machine.
even that is arguable, but okay,
That's the Lumi machine. I thought. Anyway.
Yeah. So the first people to describe a language for describing universal computation, these are these 3 guys, and all basically at the same time. By the way, these 2 guys were. This guy was a student from this guy, and this guy is independent.
That's suspicious.
Suspicious. Yes, indeed.
well, they all were at Princeton.
They were all at Princeton. Very interesting. Very curious.
Close the door.
I wonder why. Anyone want to name another person important who was at Princeton
In that time.
at the time?
Yeah, that time.
Oh, okay.
No, it has nothing to do with that.
It does have something to do with it. Very important. Very important. Do you know who it is?
The guy with gray hair.
Guy with gray hair.
Oh,
Einstein.
Yeah,
Einstein.
so- so-
Einstein was at Princeton. Does anyone know the story of why Einstein came to Princeton?
Manhattan Project?
It was not. He was a fan of Gödel. He came to Princeton because he thought Gödel was a smart guy. Okay, so Church. Anyone knows what model Church created? Alonzo Church.
Computer scientists, people.
Lambda calculus. Way of the lambda.
Next faculty meeting, we have to rework our curriculum.
Indeed. I'm gonna strong arm Rod into that discussion too. And then for Gödel, okay, Gödel's the hard one. People don't really know about it.
Well, the incompleteness theorems, we just went over that.
Universal recursive functions.
Oh, you mean the computational? Yeah.
Yes, indeed.
computational-
So all these 3 were like cornerstones of computer science.
Wait, but recursive functions were there before, right? So like as a model of computation, but just a limited. So he generalized.
You generalize it to higher order.
Okay.
Yeah.
Sorry, missed what you're asking.
Okay, so that's not really important. The one that we want to look at right now is Lambda calculus, because that's the one that's most pernicious to this diagonal right here. Now, this thing, y right here, okay. You might be asking, how is this being put into here? Right? That's kind of hard. And the answer is this thing called beta reduction. Beta reduction is the process of substituting an argument with the variable that you plugged in. You can also think of
It's
it
not a
as
variable, it's a value. Well, it's it can be a variable.
The word variable as it relates to vary is wrong technically. The correct word to use is that these are terms, and that's just a symbol, and that's it. Who cares? But the action of taking this guy and shoving it in here is called beta reduction. Beta reduction is also function application. Here's the scary part. What if, hear me out, I did that? I use function application on itself. Does anyone know of an instance where you can do this? You might know this, okay, for fixed point.
Recursion.
But like recursion where it applies itself to itself. Because usually recursion goes like this. You have a point to the base case, and then you have an arrow that goes forward like that.
How did it guess? Is it contradiction? Because it's applying to itself, right?
It is not contradiction.
No,
It is not necessarily recursion.
it's hard to guess what you.
It is self-recursion.
Well, but I mean, recursion is self-recursion. Like what you say.
Recursion is self-recursion, but it only calls the initial body of it. It still doesn't shove itself into itself. It would be more like the recursive call in a usual recursive function is a reference.
It's always a reference.
It is not always a reference. It actually can be value. So the example for lambda calculus is this thing called the Y combinator. Not that Y combinator, but this Y combinator is named after that one.
Of course.
Indeed. Because Paul Graham was a nerd. Okay, this is that Y combinator. It's popular enough for people to get tattoos of it. Okay, so what the hell is this thing?
No, but why are you jumping to Y combinator?
Because it's the hard trick.
But you don't need it for your main thesis.
I kind of do. It's the concrete example. It's the concrete example of this.
Okay.
Yeah. Because the diagonal is not a problem.
I would go
Unless
the
it-
other way. I would come to Y combinators through what you.
I guess.
Okay, that's fine. You're starting in the.
So look, if you look at this, f is another lambda. It's another function. X is some variable. Doesn't matter.
No, but it's confusing for people who are not familiar with lambda calculus. There is no f, and there is no x. Those are placeholder. It's not like you have a function that is defined somewhere. And
Yes,
It's a
yeah.
placeholder.
Put it this way, right?
Yeah. F is defined
Like,
here.
the
F is just a-
functions that nothing is named. There is no like everything is kind of by reference.
Yeah, everything is in place right here. F is over here, so the argument for F is
Oh, yeah,
going
yeah,
to the
yeah.
outside, right? And X is defined over here.
So this f can be only here because we wrote it here. It is not some kind of f that exists somewhere. It doesn't. Nothing here exists outside of this lambda.
Let me write it in usual function
It's
notation.
those placeholders.
Let me write
Well,
it-
but usual function notation makes it worse.
Does it?
It makes people think that those functions are defined somewhere.
No, I can define it like straight up too. I can define H
Well, now I'm curious. Now I
is a
want to
function that takes in an X. So that's the inner guy.
Well, but that's you assume h exists somewhere.
No, I'm defining it currently. It's okay. Don't worry about it. This mutual recursion you can do mutual recursion even in C. So don't worry about it. Is defined as f applied to x applied to x. Okay. Then y of f, and f can be anything. Anything. Okay. is equal to H applied to H.
I don't understand, h of x equals f of x, is it like, I don't get that.
X is a function.
Uh-huh.
X is
X
another
is a
function.
Okay.
In a sense, everything is a function.
Everything is a function, and
X is a function of itself.
yeah,
Which is
X is a function on itself.
Applied to itself.
Applied to itself, yeah. And F is applied to that, and then Y is H applied to itself. What's the problem? The issue is that this is an application call, and this is application squared. Oh no. So when you have application applied to itself, you now have a universal fixed point. It's very trivial to plug something in here that results in the halting problem, which we already discussed. You cannot determine whether or not this will actually halt or not. Said a different way, the status of the Y combinator is undecidable. Said another way is the number of steps taken by Y is uncountable. There's no procedure that can actually tell you how to map from a natural number to the number of steps taken by that function Y for a generic lambda. How much time do we have left? We're out of time.
You haven't even started on your essay, so
It's a lot, man. It's a lot. I don't know if there's like a version for 5-year-olds.
Yeah.
Yeah, but skipping
Skip everything. Just go to
Lawvere's paper. Yes, indeed. So Lawvere's paper over here is called Diagonal Arguments and Cartesian Closed Categories.
Share your screen for the,
Oh yeah, you're so right.
and turn off your camera if you want.
There we go. Desktop. Okay. There we go. This paper is a bunch of commentary followed by a very simple argument, relatively simple and straightforward argument over here. So you have a Cartesian category, and then afterwards you define the internal function object.
I posted the link to this tweet in reading group.
In
so
reading.
read that, highly recommend. And I will also post it to the video, to YouTube video underneath. So
Yeah, we might need like 3 parts to get this. Basically.
This one is harder, but the theorem, like you can at least tell the formulation of the theorem, right?
The formulation of the theorem. How do I even say it? How do I even say it?
So basically, you're saying, you deleted there is this identity.
Yeah,
No, there is A and Y, and there are 2 spaces or 2 sets or whatever, like types of objects, or what do you call them? A and Y, right?
Mhm.
And there are functions from A to Y. And those functions, the set of all possible functions to A to Y is that, help me with, what is it, in internal home?
Internal hom, yes, indeed.
Yeah, so it's the set of all possible functions.
All that means is that in a usual set, you have points. In another set, you have points. And there are functions between them. And usually these functions are external to the sets. For it to be an internal hom just means that this set is large enough to contain not only those objects, but also those functions natively as objects. Does that make any sense? Yeah, and then you can pair.
So that's what I meant. We can put all of the functions into that letter in the category.
Indeed, indeed, and then you can create the product between the function and its argument, right? And then you have another function called evaluate that does that. So you have an F and A. Via the product gets you to the product between F and A. Via evaluate gets you the result, where F is a map from A to B. And F here is called an internal hom, just because it lives inside the category along with everything else.
No, all you need to get out of this is there are two spaces, A and Y, and there is also a space of all functions from A to Y. And so if we assume that there is a phi that can take any function, any and each function from the set and give it to you.
Yes.
Like it's a selector. It tells you, oh, okay, I will give it to you now, just any of the functions. Then you take the identity, the diagonal product, Cartesian product that Mike was showing us. So you take this. Camera and stuff. Oh, you have the no. You're
I
well,
turn off the
you
camera.
take this and you take this phi, and phi gives you a function from that set, right? Then phi applied to here to some element, right? Will be your phi.
Well, phi of QA is the one.
Well, we'll get to Q.
Yeah.
You will have this, right? If you apply it to this. You apply it to A, but A doubles, and so you apply it to A, and whatever function this gives us is applied to A now. Phi selects a function, selects this internal home, whatever function. But now we're saying, okay, we have another function. It kind of overlaps with, and Mike will correct me. He didn't sleep since 2019.
2019 because
I only took me 1 night. I may be getting it totally wrong. And like, let's call this function GOA, right? Let's just apply some other function, whatever function.
To this guy, yeah.
To this guy, and call it GOA. But hey, you said your function is universal. It can give us any function, including G. Because G is applied to A, right? And phi gives us any function, enumerates sort of that apply. I'm not giving a proof, I'm giving definition, just a theorem statement. Or am I giving?
F is from the original set.
Yes. F is some other function from original set, any other function. You know F, but phi is this magic trick.
Yeah, phi is a function.
Phi is a magic
that
trick.
takes in some object
It gives us
and give you one of these errors. One of these errors.
Error. It gives you a function. It gives you a function from the set of all possible functions.
Selects one of them. Depending on your object, you plug in A. Now, if you have a diagonal, then you can also apply it to A over here. So instead of applying it to the application is kind of funky. It's not exactly that you're applying it to A inside of here. It's kind of applying on the outside. But you can construct this thing, which is phi A applied A.
Back to your notation.
And there's a different function A. Let's say there is. Let's construct them. And we know it exists, by the way. We prove that it exists in a Cartesian category. That is some function applied to that guy. Right? Now, the magic trick is, let's say we call, I say this, we try to find what thing gives you G, because G is a function that takes an A, so it's one of the arrows. So let's call Q that function, or that Q, that point, where phi Q returns G.
What is Q?
Q is a magical
Q
element.
is that input. Like you need to tell phi what to give to you. It's kind of like an index.
Okay.
Yeah.
Yes.
You can do a reverse lookup basically.
Yeah,
we know there's a function G. We know that it corresponds to some element inside the same category. We call that element Q.
This is like supercomputer science, just like as computer science as it gets. Very simple.
So if we take this Q and we apply A to it,
it's abstract, but it's
we get G applied to A, right? Which gets us this guy. Okay. Here's the magic. Here's where we do the magic part. A is an arbitrary thing. It's not actually like a specific thing. I haven't said what A is.
It
Okay.
can be, it can be any.
It could be anything. What if I set A equal to Q?
Q is a function.
Q is the
No, Q is an element of
index,
G.
yeah,
Q
the
is
index
an
that gives me the
element of
G. And so now when I do phi of Q, that gets me G of Q. And then we do plug it in here. And then we get F of phi of Q. Oh no, that's exactly what I plugged in. Oh no. And so you can actually reduce this back such that it is equal to this original thing. So it's a fixed point. You've constructed a fixed point. So there is some element, Q, that when you plug it into this map phi, which exists for all Cartesian categories, that results in this fixed point. Once you have this fixed point, you can do whatever the hell you want. You can make any
Can you write
undecidable.
the equality, the f of phi q equals phi q, right?
Yeah.
Like,
So-
I mean, right here or right here.
Yeah, F of, equal to
Phi q. Yeah.
phi Q. There we go.
But then that means, and we didn't define f, we didn't constrain f, right?
So F can be any function you want.
So we just say, we just proved that for any function in this set, sorry for overloading, there will be always a fixed point. It's like, it has to be, otherwise phi doesn't exist. If phi exists, then for any f, there should be a fixed point. That's the, that's the Lawvere. How do you pronounce his name again?
Oh, Lawvere.
Lawvere, yeah.
Lawvere.
That's Lawvere's theorem.
Yeah.
If you have if you are able to enumerate, phi enumerates elements. If you're able to enumerate functions from set A to set Y, and you have allow this relationship, identity product or diagonal, then all of your functions must have fixed point. And now this whole thing enters.
Yeah.
Let's flip it, and it's if and only if.
Yeah,
And
so we
so-
can construct the contrapositive version. So if these functions has a surjection from A, that's what we use at the start, from A to Y to A, which are the functions, the internal homs between Y to A to Y, right? So if having this means that your function has a fixed point, means that F has a fixed point. Then, if F doesn't have a fixed point, then there can be no surjection here, right? Because it's an if and only if. You can flip it around. Does that make any sense? I can repeat that too. Yeah. So the original assumption that we had is that there exists a surjection between these two. There's a way to plug in a function and get back an element A between these two, right? If this exists, then
Or in reverse, phi does reverse, right?
yeah, phi does look up of A to Y. Yeah.
Which
Then,
is the same, I mean, for our purposes.
then F, which is things that does this,
All of the arrows.
has a fixed point. A fixed,
It has to have a fixed point. That's basically what we're talking.
yeah.
All of them. And
So
then
the-
any f.
Yeah, so the contrapositive version is just not on both sides. So if F doesn't have a fixed point, then there can be no surjection. You can't have a surjection like that. You can translate this back to like there's no
I
lookup.
think we have to jump to people are like, you will understand why we need this.
Yeah.
This now proves everything.
Yeah, so let's look at Cantor's theorem. Huh?
Yeah, this is the set of all functions from A to Y.
A to Y. Y is an arbitrary object, including A.
Is it like phi?
No, phi is a function.
Phi is a function, but hilariously,
Outside.
hilariously in category theory, things are loose enough that Y can in fact be phi. Things are there's no rule banning
Y
it.
can include. phi.
Yeah, Y
Those
can
are-
include
Those
phi.
are like sets.
Phi is one.
Y can contain phi in a sense, right?
Y is a symbol that can be specified
Okay, it's
into.
a symbol.
It's a symbol that can be specified into anything you want, including phi, including A itself, including anything else.
Yeah,
Okay,
A is
so
fine because then it's a self.
so in the case of Cantor's theorem, you let Y be the special set 0, 1. The other name for this set is Boolean, by the way. And your function f of 0 equals 1 and f of 1 equals 0.
The function is not.
That is not, right? It takes in 0 and spits out 1, takes in 1 and spits out 2. This has no fixed point, right? Because it can't be, there's nothing you can plug into f that returns the argument. This function has no fixed point, and therefore no set surjects onto that, the map from A to bool, or A into 0, 1. Okay.
Yeah, this is just a notation for all possible functions that take elements from A into Boolean.
Does it look like Halting problem?
It does look like
they're
the
all
whole,
the same.
yeah, they're all the same. Yeah,
They're
eventually.
all one single problem.
Yeah.
So.
There we go. This is the original Cantor's theorem. No set
Q of A is
surjects.
power set.
Yeah, power set. No set surjects onto its power set. Done. Finished. You're done. No, don't worry about that. So here we go. We have another thing. Cantor's uncountability of R. Reals in the range 0 to 1 are functions from n to the set of digits 0, 9. The successor mod 10 on that has no fixed point. Because if you do, how do I do this? How do I do this?
So what you're saying is basically this thing that you wrote here where you said A maps to Y of A, you're proving like that the left-hand side is false, so that means we know the right-hand side is false.
Not specifically here. Well, here, yeah, in this line. Like,
You've
if
shown
and
it.
only if. Yeah.
Actually, no, I don't think it's an if and only if. I think it's just it's a forward direction.
No, but like, how do you go backwards?
Contrapositives flip both the conclusion and the sign. Yeah, so that's a contrapositive. Because that's how first order logic works. If you have A to B, the contrapositive is not B implies not A. Yeah, there we go. Okay. Yeah, the reals are uncountable.
Well, that's an if and only if.
No, it's not. Because you can't conclude, for instance, that not having a surjection over here means that there is no fixed point. You potentially could have a fixed point without needing the surjection. We've only proven one direction. Yeah. Yeah.
Okay, so you showed it for these two examples, and then what? Now the halting problem.
Yeah, the halting problem is you replace bool 0, 1 with instead the two states, halt and doesn't halt. And F is the swapping thing that happens between, oh God, this requires like knowing what the Turing proof does with like the
Well,
oracle.
it feeds the program to itself.
Yeah. You just feed the judge that does. The way it works is you assume there is an oracle that tells you whether or not the program halts or not, and then you plug the oracle into itself. Yeah.
No, but you assume also there is a function f that flips the value. If the oracle tells you hold, the f flips and says no, doesn't hold.
Yeah.
And then you get exactly this construction.
Yes. So it's
this construction. This is the oracle, and the phi is the oracle, f is the flip. Like that's how Turing constructed his proof. Assume this thing exists. It tells us if program holds or not. Then f is this f function flips the value, and so by that Turing constructs ingeniously, not having the Lawvere theorem, constructs this proof. Not a proof. Constructs contradiction. He says, well, if the program holds, then we immediately flip that it doesn't hold to show that it holds. But and in the other way also, it's kind of like the same thing.
It's funky. Yeah, same thing with Tarski's paradox. You cannot have a truth predicate. So a truth predicate is a predicate that says whether or not a theorem is true or false. If you define this for a language and it is total, then you have a contradiction, because then you can define a truth predicate for the statement, this statement is false. And that statement cannot have a predicate that's true or false. So you cannot have an internal notion of truth, and it's the same argument. And same thing for Gödel incompleteness, the first one. You use the exact same trick. And they're all the same theorem. They're all the exact same theorem, except you need machinery, you need domain-specific machinery to get it done. For Turing machine, for Turing's undecidability, so Turing halting problem, you need to construct a Turing machine. For Gödel incompleteness, you need the hell construction known as Gödel numbering. Gödel numbering is like utterly...
But you still need it.
Yeah, you need the machine, yes, but the core argument being made is the Lawvere argument. And the Lawvere argument is very short and very straightforward. It requires maybe like 5 introductory lectures into category theory, as opposed to, how long is Gödel's proof? Gödel's first incompleteness.
His construction, so he can enumerate every logical program, right? Or every logical statement.
Every theorem, you can enumerate them because they're just, you can encode.
It's theorem, this is just a statement.
Yeah, every sentence is the word he used. You can enumerate every single sentence and biject it to the natural numbers. Gödel's first.
He offered the construction.
Yes, and then you can find the special statement G. There's no way. Oh my God, 300 pages as an introduction. It's a lot. Okay, that's actually not that bad. No, there's no way this is easy. It's that easy. Yeah, Gödel's original proof is way longer. But the broader point.
Just summarize everything.
The broader point is that category theory lets you spot specific constructions via morphisms that are shared across a bunch of domains and arguments. So hidden within Tarski's proof, two of Cantor's proofs, Turing's proof, Gödel's proof, is a specific argument. And they all call it the diagonal argument. Actually, Tarski didn't call it the diagonal argument, but all the other ones call it the diagonal. That has an exact correspondence in category theory. And the one in category theory actually tells you why this construction is so problematic. And it doesn't confuse you, because Gödel's incompleteness, people think that it's a statement about, they don't think it's about the diagonal, they think it's about that piano arithmetic, which is just like real number, natural number arithmetic. But in fact, it has nothing to do with piano arithmetic. It all has...
still, your theory has to be complicated enough
to describe piano arithmetic, but the actual thing being smuggled in is the ability to describe the diagonal.
You think Gödel knew this? Or...
Gödel did not know this. Yeah. One person that almost knew this, predating all of them, is Wittgenstein. Wittgenstein almost understood this.
He wasn't predating them. He was around the same time, and in the 50s he wrote his whatever the...
No, Tractatus was before 19th century. 1921. Okay, yeah, you're right. He's about the same. Yeah.
It's like the same people hanging out at the same Twitter.
Yes. Yeah. He had gotten into an argument with Turing at Princeton, and that was an inspiration for Gödel to eventually speedrun his way to the to his incompleteness theorem.
And that's how science works. We communicate, we regurgitate half digested ideas, and then one lucky person puts them together, and everyone put, well, but different communities will point to different people.
Yeah,
that's how you get famous. But
there are more. Probably stop the share or the recording. Yeah.
Thank you, online people, for coming here and listening to this fantastic mess. Next time we'll be more organized, but this is a bit of spice of computer science in our AI and neuroscience of VLOG.
Yes.